We have all been there. You reach for a flashlight in the dark, click the switch, and nothing happens. Older, traditional flashlights often generated enough heat to make the front glass hot to the touch. By contrast, the flashlight built into a modern smartphone remains completely cool, even after minutes of use. Electricity is a physical flow of energy that requires a continuous, unbroken path to travel from a power source, through a device, and back again. This completed loop is a closed circuit. A failing flashlight indicates that this physical path is interrupted somewhere inside the casing. This interruption creates an open circuit, which halts the flow of energy immediately. Every basic circuit relies on two components to operate: a power source to push the energy, and a control mechanism to regulate that movement. This compares water flow to electric current. A pump pushes water through a pipe, while a battery pushes electrons through a wire. An off switch creates a gap, stopping electrons like a closed valve. Clicking on bridges the gap, resuming continuous flow. Understanding this flow allows us to diagnose electrical failures. But to fix the flashlight, we have to look at what happens when that energy reaches the light source. For over a century, flashlights relied on incandescent bulbs. Inside the glass dome of these traditional bulbs is a delicate, tightly coiled wire called a filament, usually made of tungsten to withstand high temperatures. As electrons are forced through this incredibly narrow tungsten wire, they generate massive physical friction. This produces intense heat, but it is highly inefficient. Most energy becomes heat rather than light. Eventually, the brittle filament snaps, creating a permanent gap that halts the flow. Because the wire is physically broken, the circuit loop is severed. Electrons cannot cross the gap, requiring the replacement of the entire bulb to restore the flow. Modern flashlights use a light-emitting diode, or LED. Unlike incandescent bulbs, an LED does not rely on a burning metal filament to create illumination. Inside an LED, electrons pass through a special semiconductor material. As the energy moves through this substance, it emits light directly, which allows the device to remain cool to the touch. LEDs operate on a principle called polarity. As seen here, electrons flow through the junction block in one direction to emit light. If the flow attempts to reverse, it hits a solid barrier. The LED acts as a one-way turnstile for electricity. If you insert a battery into an LED flashlight backwards, the LED blocks the current. The bulb is functional. The failure is simply a directional mismatch between the battery and the LED's one-way gate. The LED's strict one-way rule and low heat output enabled the development of more compact and complex electronics. To manage these directional components, engineers developed a standardized visual language. Drawing detailed 3D pictures of every battery and bulb is inefficient. Engineers use a simplified visual language to draw blueprints quickly and accurately. Physical objects translate into 2D universal symbols. A 3D battery morphs into a long positive line and a short negative one. A wire switch becomes an angled line for an open circuit. The LED symbol features a directional triangle with radiating light arrows. Today, these standardized symbols allow anyone to read, troubleshoot, and safely build electrical blueprints across any language barrier. Using this schematic, we diagnose the flashlight. Current is visibly blocked. The switch is closed, so it functions. However, the cell's long line pushes current against the flat wall of the LED triangle. Flipping the cell aligns the polarity, allowing current to flow. Scaling this logic up reveals real-world energy impacts. Cities replaced grids of incandescent streetlights with LEDs, saving billions of watts of electricity annually. By mastering the physical path of electricity and the symbols used to map it, you gain the foundational language required to engineer the modern world.